Waves appear everywhere. Shock waves, ocean waves, sound waves, electromagnetic waves, and there are a number of derivations of the wave equation with different physics as their starting point. In this video, we'll derive the wave equation from Newton's second law of motion. There is a derivation starting from the ideal gas law on the Berkeley Science website, and in a later vid on Maxwell's equations, there is a derivation starting from Maxwell's equation. We start with a string under constant tension. Think of a guitar string stretched between two posts. The string tension is T, a force in units of newtons. We will include in the model the effects of an external force applied to the string, represented by the function f of t, x, with units of newtons per meter. The displacement of the string at time t in location x is given by the function u of t, x. Consider the forces acting on a control volume of the string, a section of the string of length dx centered at x. At the point x plus dx over 2, the string is being pulled with a force t, and the direction of the force is tangent to the string at that point. We will assume that the string only moves vertically, and so we are interested in the vertical component of force on the control volume, which at x plus dx over 2 is t times the sine of the angle that the tangent to the string makes with the x-axis, theta 2 in the diagram. Similarly, the force on the left end of the control volume at x minus dx over 2 is t, and the direction of the force is theta 1 plus pi. The vertical force is t times the sine of theta 1 plus pi, which equals t times the sine of minus theta 1, which is minus t times the sine of theta 1. We assume that the angles theta 1 and theta 2 are small, and so we can use the small angle approximation that the sine of theta 2 equals the tangent of theta 2, which equals the spatial derivative of u at x plus dx over 2, and the sine of theta 1 equals the tangent of theta 1, which equals the spatial derivative of u at x minus dx over 2. Now we use Newton's second law of motion, which states that the vertical acceleration of the control volume equals the sum of the vertical forces acting on the control volume divided by the mass. The vertical forces on the control volume are the vertical forces at the ends of the control volume plus f of t, x times dx, and the mass of the control volume is dx times rho, the density of the string. So we have equation 1. Taking the limit as dx goes to 0, we have the differential equation model. The acceleration of the string at point x at time t, i.e. the second derivative of u with respect to time, multiplied by the string density, equals t times the second derivative of u with respect to x plus f. We've derived the differential equation model. The next step is to make the Fdm substitutions. Here is the primary Fdm substitution and its derivation, just as a reminder. Both derivatives in the model are second-order derivatives, so the substitution from the previous slide is used for both, and the result is equation 1, which is solved for u superscript n plus 1, that is u at time t n plus 1, to get the computational equation at the bottom of the page. We know that a second-order time derivative represents acceleration. What does a second-order spatial derivative represent? The answer is curvature. Note that the Fdm substitution for a second-order spatial derivative, shown at the top of the page, can be rewritten as a constant times the difference between the average value of the function at the endpoints of the control volume between x minus dx and x plus dx, and the value at the middle at x. The diagrams show three possible cases. If u of I equals the average of u of I plus 1 and u of I minus 1, the estimate is 0, and it corresponds to u being linear or nearly linear near x. If u of I is greater than the average of u of I plus 1 and u of I minus 1, the Fdm estimate is negative, so a negative second derivative corresponds to u being concave downward near x. If u of I is less than the average of u of I plus 1 and u of I minus 1, the Fdm estimate is positive, so that a positive second derivative corresponds to u being concave upward near x. We've derived the model, we've made the Fdm substitutions, we're nearly ready to go. What are the fine points? First, we have the model and the computational equation, and the computational equation translates directly into MATLAB as shown. Since the time derivative was second order, to calculate the values of u superscript n plus 1, that is at time t n plus 1, we need the values of u for time tn and tn minus 1. So we need to initialize the values of u for t1 and t2. Then we can compute the values for t3 and beyond. This is no problem because we will initialize everything to 0. How about boundary conditions? A guitar string is usually fixed at both ends, and that corresponds to Dirichlet boundary conditions at both ends. We'll also do one problem where we leave the right end free using a Neumann boundary condition. Where does the wave come from? We need some input. So to get it, we will override the boundary condition on the left end of the string to introduce a wave into the string. Once the wave is on its way, we'll reinstate the boundary condition. In the example that follows, we first introduce a sine wave and then a square wave. Watch what happens when they meet. Try making a prediction. The assignment is to duplicate the results in the video and then to run the program with a Neumann boundary condition on the right boundary. You can see what that should look like in the clip following the program outline.